High-speed microcontroller-adaptable PWM controllers. Welcome to this module on high-speed microcontroller-adaptable PWM controllers. This module provides an overview of the MCP1631 high-speed pulse width modulator and discusses its key features and its typical applications. The MCP1631 MCP1631V offers both current or voltage mode, respectively, for high-speed microcontroller-based pulse width modulation, ideal for programmable switched mode battery charging for intelligent power system needs. The MCP1631 MCP1631V inputs were developed to be attached to the I/O pins of a microcontroller for design flexibility. When combined with a microcontroller, the MCP1631 will control the power system duty cycle, providing output voltage or current regulation. The microcontroller can be used to adjust output voltage or current, switching frequency, and maximum duty cycle, while providing additional features making the power system more intelligent, robust, and adaptable. The MCP1631 MCP1631V is a combination of specialty analog blocks consisting of a pulse width modulator, PWM, MOS FET driver, current sense amplifier, A2, voltage sense amplifier, A3, overvoltage comparator, C2, and additional features, shutdown, undervoltage lockout, overtemperature protection. For the high voltage options, an internal low dropout regulator is integrated for operation from high voltage inputs. On the MCP1631HV, MCP1631VHV. The MCP1631 MCP1631V device family combines the analog functions to develop high-frequency switch mode power systems. When used in conjunction with a microcontroller, the MCP1631 MCP1631V will control the power system duty cycle to provide output voltage or current regulation. With the oscillator and reference voltage as inputs, a simple interface to a microcontroller is available with the MCP1631 MCP1631V to regulate output voltage or set current and switching frequency. The MCP1631 MCP1631V generates duty cycle and provides fast overcurrent protection based off various external inputs. External signals include the input oscillator, the reference voltage, the feedback voltage, and the current sense. The MCP1631 MCP1631V has built-in undervoltage lockout, UVLO, that ensures the output V sub EXT pin is forced to a known state, low, when the input voltage is below the specified value. This prevents the main MOS FET switch from being turned on during a power up or down sequence. From the internal block diagram, we can see that the MCP1631 MCP1631V is integrated a pulse width modulator, PWM, MOS FET driver, current sense amplifier, voltage sense amplifier, and overvoltage comparator into one package. Therefore, it is a highly integrated, high-speed analog pulse width modulator. The family is also available in different package options, including small 4x4 QFN and standard 20-pin TS-SOP and SSOP. The MCP1631 MCP1631V can be used to develop intelligent power management solutions. Typical applications include a multi-chemistry battery charger used to charge lithium-ion, nickel metal hydride, or nickel-cadmium batteries. Therefore, it simplifies the end-user equipment design. The internal PWM of the MCP1631 MCP1631V is comprised of an error amplifier, high-speed comparator, and latch. The high-speed analog PWM is used to control the power switch on and off times to regulate the output of the converter. For applications that operate from a high voltage input, the high voltage HV devices, MCP1631HV and MCP1631VHV, can be used to operate directly from a positive 3.5 volt to positive 16 volt input. For the HV options, an internal low dropout regulator is integrated for operation from high voltage inputs. The MCP1631 family is ideal for power conversion applications that require medium to high levels of intelligence and high speed, where the application can be operated at any frequency up to 1.0 MHz. Typical applications include programmable switch mode battery chargers capable of charging multiple chemistries like lithium-ion, nickel metal hydride, nickel cadmium, and lead acid, configured as single or multiple cells. By combining with a small microcontroller, intelligent LED lighting designs, and programmable single-ended primary inductive SEPIC topology, voltage and current sources can also be developed. The MCP1631 multi-chemistry battery charger reference design is a complete standalone constant current battery charger for nickel metal hydride, nickel cadmium, or lithium-ion battery packs. When charging nickel metal hydride or nickel cadmium batteries, the reference design is capable of charging 1, 2, 3, or 4 batteries connected in series. The board uses the MCP1631HV high-speed analog PWM and PIC16F883 to generate the charge algorithm for nickel metal hydride, nickel cadmium, or lithium-ion batteries. The PIC16F883 microcontroller can be used to regulate output voltage or set current, switching frequency, and maximum duty cycle. The MCP1631HV generates duty cycle and provides fast overcurrent protection based off various external inputs. The reference design is user programmable using onboard push buttons. The board provides a constant current charge, nickel-based chemistry, and constant current, constant voltage, lithium-ion, with preconditioning, cell temperature monitoring, nickel-based, and battery pack fault monitoring. Also, the charger provides a status or fault indication. For nickel batteries, the charge cycle begins once a battery is detected by regulating a small current or conditioning current into the battery pack. If the cell voltage is above 0.9 volts per cell, it is safe to charge the pack with a fast charge or high current. When the battery reaches capacity, cell manufacturers recommend a top-off charge to complete the charge cycle. The charge profile for lithium-ion batteries starts with cell qualification. The cell voltage should be greater than 3.0 volts per cell before initiating a fast or high current charge. If the cell voltage is less than 3.0 volts per cell, a low-value conditioning current is used to start the charge cycle. As the battery cell voltage rises, it reaches the maximum voltage value before it reaches full capacity. In the figures, we can see that there are significant differences in the charge profile between nickel batteries and lithium-ion batteries. A multi-chemistry charger must be able to implement the proper profile and proper termination methods. A battery charger and power supply have a lot in common, delivering a regulated output from a varying input. Many switching regulator power topologies exist. Buck, boost, a SEPIC converter is commonly used. It has advantages over buck and boost converters when used in battery charger applications. The capacitor, CC, provides DC isolation from input to output, which results in less power components and a safer battery charger. The inductor at the input intends to smooth input current and reduce source noise. A single low-side switch reduces MOSFET drive and current limit protection complexity. The development of an intelligent multi-chemistry battery charger starts with the microcontroller. The SEPIC converter is a microcontroller controlled current source. To increase current, the microcontroller simply increases the V sub ref input to the MCP1631, and to decrease current, the microcontroller decreases the V sub ref input to the MCP1631. By implementing the charge algorithm in microcontroller code, the charger can be adapted for multi-chemistry. The microcontroller measures the battery voltage using an analog-to-digital converter, AD, computes the desired charge current, and adjusts the SEPIC controlled current source up or down. The MCP1631HV provides a regulated bias voltage for internal circuitry that is available for biasing the microcontroller and other components. The analog PWM starts with the oscillator input, typically a microcontroller PWM output or simple clock output at 50% duty cycle. When the oscillator input is high, the V sub EXT output is pulled low and N-channel MOSFET driver is on. A new cycle is started when the OSC sub in input transitions from a high to a low. The internal N-channel MOSFET driver turns off and the P-channel MOSFET turns on, driving the V sub EXT pin high, turning on the external N-channel MOSFET. Current begins to ramp up in the external CS sense resistor until it reaches 1/3 of the level of the error amplifier output voltage. The error amplifier is configured as an integrator, so any difference between its inputs V sub ref and V sub FB are quickly removed. To sense battery current for regulation in an SEPIC converter, the secondary winding of the coupled inductor can be used. The average current flowing through the secondary winding is equal to the current flowing into the battery. MCP1631 integrates an inverting 10 volt per volt gain amplifier to increase the battery current sense signal. The microcontroller sets the V sub ref input to the desired current level. The MCP1631HV uses the V sub ref input as a reference for regulation. Using the internal microcontroller ADC to sense battery voltage is a popular approach. An issue with this technique is the ADC requires a low source impedance to perform accurate readings. Low source impedance requires low resistance values that draw excessive quiescent current from the battery. The MCP1631 integrates a low current amplifier, A3, configured as a unity gain buffer. The buffer output impedance is low, driving the SAR-AD converter while consuming very little quiescent current. A high-value resistor divider is used to drop the battery voltage to an acceptable range. R1, R2, and R3 values are selected to minimize the drain on the batteries, typically drawing on the order of 1 microamp. The microcontroller reads the ADC, calculates the current setting, and adjusts the V sub ref input to regulate current. The MCP1631 family integrates the necessary blocks to develop an intelligent, programmable battery charger or constant current source used for driving high-power LED applications. Here we describe the design of high current switching battery chargers using the MCP1631. Depending on input voltage range, there are two versions of the device that can be used to accommodate a very wide range of input voltages. The MCP1631, MCP1631V family integrates features that are necessary to develop programmable current sources. The SEPIC rectifier blocks the reverse path, preventing battery leakage. The internal MCP1631, MCP1631V analog components are used to regulate the microcontroller programmed current, protect the charger and battery from being exposed to high voltages, limit peak switch current, and limits the device junction temperature to 150 degrees Celsius, preventing catastrophic failure for over-temperature conditions.